Swayam Prabha. Digital India. Educated India.
Hi, welcome back. So, we were doing this example, we started doing this example where the mean free stream velocity of a turbulent flow over a flat plate is given to us, right? The friction RE is 1000. So, we were trying to see the velocity profile for the resultant turbulent boundary layer, right? And we really need to study that, okay? So, we started out basically by saying at the wall shear stress is entirely a viscous contribution. We know that, from our previous studies. So, essentially the term, if you look at the Navier-Stokes equation, this term actually, the mean of that doesn't really contribute much to the the shear stress at the wall. It is primarily the mean component of the velocity, right. So, this is the term that we usually look at. As a matter of fact, what we should be looking at is this, okay. So, right, and so again the wall shear stress is given by the usual description, right, and y is equal to 0. In this case, the u mean is given to us as an expression which is here. So, I take a derivative of that in the y direction, and what we got from last time is tau w, is shear stress at the wall, is 100 gamma into nu, okay. Rho into nu, I keep saying gamma, okay. Then now, what exactly are we talking about? When I say friction, Reynolds number and things like that, right. So, this is from the law of the wall, right, and we know that right near the wall it is the there is this length scale which is governed, which is governed by scales which are independent of the free stream velocity and density of the fluid, right. So, so we can therefore develop exclusive length scales for that, which is what we are doing here, okay. And so then we come up and say friction velocity. So, this is for the specific, basically inertial subrange, right. So, we go there, and and then we figure out the values, and what we see here is, so we got these from last class, okay, and so we got the corresponding velocity, right, the length scale, right, and this is of course the length of this is the height of the boundary layer, thickness of the boundary layer, let's put it that way, and this is the viscous length scale that we are talking about here, okay. And then of course, you have the friction RE and stuff. Now, the nu, okay, for air is given to be this. So, let us write out these values first, okay. Let us write out these values first, and let us see where we get, okay. All right. So, now let us get u tau. Right, is equal to 10, right, under root right. So, I am going to write this as how about that, okay. So, what I get is essentially or rather right, that is more appropriate. So, then this is actually equal to Okay. Or you can say this is equal to this. Okay. So, or u tau is equal to so these are values for a boundary layer which is formed by air, right. So, this is u tau for the given velocity profile. This is what we get. Okay, u tau is this. Then next is the delta v. Okay, delta v is equal to right by 10. Okay, this is actually equal to okay, therefore delta v is equal to right, and this should be meters, of course, this should be meters per second. That okay, then okay, let's go to the next page and let's do the delta and the RA. Okay, so let's go to the next page and let's say now delta is equal to delta is equal to delta is equal to delta by delta v. Okay, now let's do this first. Okay, so delta is equal to okay. Now this is interesting because RE tau, right, is actually equal to delta by delta V, right. This is what we have now, and here, okay, is this, then this is equal to 10 to the power 3, which is given to us, right. Therefore, delta is equal to 1000 times delta V, right. Did you calculate delta V? Yeah, delta V we did calculate, right. Okay. Okay, so this is therefore equal to 10 to the power 3, right, and delta V is, well, let's just say it is right by 10, right. So this is basically, therefore, delta is equal to 0.387. Okay, so essentially that, so I have this delta, I have the delta value, I have the RE tau value, okay. I have a u tau, I have a delta V here, okay. So what are we saying, right? So what are we saying? So what we are saying is this, so that if we have right? Okay, so let's just say at some location, right, and this is my boundary layer. This is my turbulent boundary layer, where this of course is free stream velocity, right? And what is the height of this? Right, the height of this is delta, right, which is 0.387 meters. This is delta, right, and delta V is actually this, right. It's actually 1/1000th of delta, right. I mean, you can see that here itself. So delta V is actually delta by 1000. Okay, so then we have a layer here. Okay, let's just say we have a height here. I'm exaggerating this, okay, and this height okay, this is delta, right, and this is delta V, right, which is the viscous scale, which is delta by 1000. Okay, that's delta V, right, and in this viscous, right here, so essentially this is the, let's sort of remind ourselves what the law of the wall was. Okay, let's just, I'm going to just read it out, okay, exact how we had written it down. So we'll just sort of write that down. Yeah, I mean, just talk about it. Okay, just give me a sec. Let me pull that up as to what we wrote. Okay, right. So the thing was that at high Reynolds number, close to the wall, there is an inner layer, right, in which the mean velocity profile is determined by viscous scales independent of boundary layer thickness and free stream velocity, right. This is the Prandtl in 1925. This is the law of the wall, right. So and for that particular layer, this inner layer, the inner viscous layer, right. So inner viscous, this is the viscous sublayer, right. So where we calculate for that particular layer, we calculate separate length scales, velocity scales, and the Reynolds number. So which is what we did just now. Okay. So then in this layer, of course, okay, we have the U tau, right, which we found to be about 0.4, I think, right, 0.04, right. So this was the U tau, right. Then in here, so essentially I can say that U tau is equal to about this U tau. Here of course it is U. Okay. Now this is the turbulent zone. This is a turbulent boundary layer, and this is the viscous subrange. You can say this is the viscous subrange. So this is the viscous subrange. So what am I talking about? This is that viscous subrange. Okay, so that's the viscous subrange we are talking about, right? And U tau is this value, right? Now, also, yeah, so essentially that. Okay. Now U tau, Uy in the turbulent zone, right, in this zone. Now I didn't give any definition for that, right. Now remember what we did last class, we did something like this here. So we did something, this was also Prandtl's for turbulent flow below 10 to the power 7, which seems to be our case. He defined something called a 1/7 law. So this is the velocity, right, in terms of in a turbulent boundary layer, right. So this is also something, this is exactly what we were doing last class for this problem using a pipe, right. So using this 1/7 law, so one could use this, one could actually use Prandtl's 1/7 law here, okay, 1/7 law here in the turbulent zone, and so that could be the curve, okay. So what in this particular case, for the given velocity, for the given velocity profile, right, we were able to find out resulting turbulent boundary layers indicate detailed aspects of so that's what we are doing right now, right. So for the friction layer, right, or the inertial layer or the viscous layer sublayer that we have in the boundary layer, so we have found out its thickness, we have found out the velocity in that, and the Reynolds number is of course given. So let's write that down as well. So in here the Reynolds number, right, is equal to 1000. Okay, so that's the turbulent boundary layer that we just talked about. Okay, all right. So I think that's all. I think that's all the information. Okay, one more thing. Yes. Now let's do one thing here. Okay. Now given this, okay, now y plus, it was something that we defined. Okay, if you go back and relook at things. Okay, now y plus, I'm going to do it here. Okay. Okay, now y plus, okay, is equal to y by delta v. Okay, in this case that is equal to y, and delta v is essentially correct, right. So this is equal to y. Okay, right. Now then we have these, we had written these out earlier. Now y plus is equal to 50, right. It means what? It means y is equal to 50 by 2.6 into 10 to the power 3, right, which is about 0.02 meters. Okay, so we can define this length scale y plus in such a way. This is for the turbulent length scale. Okay, this is for the turbulent boundary layer, for the complete boundary layer. Okay, so then we had this definition earlier, and we're going to write that. So if y plus is less than 50, right, or essentially y is less than 0.02 meters, right. So that means it is the viscous wall region. So this is for this particular case, where if distance from the wall is less than 0.02 meters, okay, 2 centimeters actually. Okay, then if y plus is greater than 50, which means that y is greater than 0.02 meters, right, that's the outer layer, right, that is the outer layer. Okay, then y plus is less than 5, which means y is less than 0.002, right. This is the viscous sublayer. Right. So, if you see in this problem, what was our delta V? So, delta V is actually, so delta V is this, which is definitely much less than 0.002 here for in this particular case, right. So, therefore, that basically corresponds to, so delta V that I have here actually corresponds to the viscous sublayer, right. And till about 0.02 we have a viscous wall region, the rest of it is outer layer, right. So, I think that is it. I mean, that is all we can define. So, we can mark these regions in this plot as well. Okay. So, we can do that. Okay. All right. So, fine. So, that is that really. Now, let us look at something, an interesting sort of a problem, right. So, interesting sort of an example, okay, where we are going to talk about say around jet. Okay. So, let us look at that. Okay. Now, let us just say this is another, this is an example. Okay. Now, the following jets at standard temperature pressure at location x naught is equal to 25 meters, right. So, let's see what information we can get. So, essentially we need to comment on u naught by uj and right. So, the central velocity, right, by the jet velocity, and this is r half is the jet half width or the spread basically, right. So, let us see. Okay. Okay. No, this is not the solution. Wait, I mean, so these are, there are actually 5 jets. Okay. What are they? So, let me sort of tabulate them instead of writing it so many times. Okay. So, this one is okay, let us just say this. Okay. Now, I am going to tabulate this for easier stuff. Okay. So, this is fluid, like what fluid are we talking about? Okay. Then we have density rho, okay. Yeah, well, kg per meter cube. Okay. Then jet velocity, uj meter per second. Okay. Then we have exit dia d in meters, okay, and the dynamic viscosity. Coefficient, it is in Newton second per meter square. Okay. Then, so number 1 is water, okay. Density is 1000, uj is 10, this is 0.25 dynamic viscosity is 0. This, right? Then the second one is air, density is 1.32, jet velocity is 100, exit dia, and nu is 1.205. Okay. Now castor oil, this is castor oil. Okay. Now density is 956, Uj is 2, D is 0.5, and this is 0.65. Okay. This is fuel oil. Okay. Then rho is 890, Uj is 25, D is 0.15, and this is 1. It's about 1. Okay. Okay. And kerosene, right? So this is 820, this is 250, this is 0.1 and 0.00164. Right, so we have these 5 jets here, right, and we need to essentially comment on these U naught by Uj and R half. Okay, so what can we do? Right, so how do we comment on this, or what is it that we need to look at? Okay, so first I thought that let us look at the Reynolds number. Okay, that will be nice to look at, and we will write that down here. Okay, so we will write down the Reynolds number here, so which is equal to rho phi d, right. So this will be basically Uj by mu, right. So we can do that. So let us calculate that. Okay, let's go and calculate that. Right, we have these jets. So Reynolds number is, for the first case, right, rho Uj is 10, dia is this, by nu, right. So this is equal to 3 million actually. Okay. Then the second case, Ra is 1.32, V is 100, D by 1.205. I think you should be doing this along with me, or you sort of stop the video, do this yourself and come back and cross check. Okay. There's no point gaping at the board or looking at the instructor. It's best to do it yourself. And that's the only way it's going to register. Me telling you like this is not going to register. Okay. So then for the third case, it is 956 into 2 into 0.5. The reason I'm writing out this way is that if at all I have made a mistake, then where the mistake is, it's easier to track. So I'm sort of writing it down. So sometimes there is a mistake in maybe I took the wrong dia or something from another jet. Okay. All right, then again here also rho uj diameter and nu, which is equal to about 3,500, this is 1,500, okay. Eight rho uj diameter and mu. $12.5 million. Okay, so let's write that down. Okay, let's write that down in the previous case. Okay, these are calculated, so let's just say these are calculated, the rest of it is given. Okay, so we calculate this and this comes out to be 3 into 10 to the power 6, 5.45, about 1,500, about 3,500, and this is about 13 million. Okay, so the point is that we have all these different Reynolds numbers. Then what do we expect these jets to do, right? Does that mean that because the Reynolds numbers are so spread apart, right, their behavior in terms of how the jet will form, right, as to how much R half will be, or how the velocity will vary, right, the mean velocity will vary. So, is or center line, mean center line velocity will vary, will that be different, you know. So, it seems obvious that yes, Reynolds number is so spread apart for these jets, and everything seems to be, because there is a density, there is a velocity, the dia, everything is different for these jets, right. So, that means if I have to, with all this understanding so far of turbulence studies, right, and now that you know that you can solve equations, right, in more than one ways, and then of course you cannot solve a lot of those equations because of the complexity, even computational cost involved, right. So, you are aware of that now. So, in that context, so these 5 jets seem to be like starkly different from each other, if you see. Then what is actually, how can I comment on this u naught by uj and r half and so on and so forth. Okay, right, that is the question. So, now let us go to the next. Now, we know, right, we know from our studies earlier that we had got 2 of these, right. So, we had got 2 of these empirical constants, right, where S was the spreading rate, right, and 1 by B was actually slope, and 1 by B is actually slope of the curve uj by u infinity versus r by x, I think so. Okay, actually x minus x naught, because x naught is the start point. Okay, so let me let us revise, sort of revise that for a little bit, if you remember. Okay, so yeah, that is correct. Actually, sorry, this is actually x by d. Let's just say okay. So, this is something. So, what we had done, I'm going to quickly remind you said, so I'm going to, and this is actually, so then we said B is an empirical constant, right? And slope of the curve, and this is also the decay constant. So this is the velocity decay constant, and that of course is S is the spreading rate. So let me just quickly sort of remind you about that. So this was from an experimental data set which we had, right? So this is essentially x by d, okay, and this is uj by u naught, right, mean central velocity, and we had found that okay. So you had several of these data points. So these were essentially experimental data points, and if you drew and you could actually draw a line through that, right, which would actually intersect the x axis here. So and I'm going to call that an x naught by d. That's what I meant, x naught. Okay. So then I can take essentially, let's just say this point is A, right, this is location A, and this is an arbitrary point, say P, right. Then the coordinates of A are x naught by d 0, and P, the coordinates are okay. So P is x by d and uj by u naught, right. Then slope of the line is basically uj by u naught, right, by x by d minus x naught by d, right, and this is denoted as 1 by b. This is something that we had done earlier. So, or uj by u naught, right, is equal to x minus x naught by d into 1 by b, right. So that's something we had come up with, right, and of course the other one, so that's basically B. This is what we had found out, right, and S is actually we basically said S so essentially how the jet huff width changes over time. I mean that is what spreading rate is all about. And then if I have a spreading rate which I call as S, right. So this is a detailed I mean the derivation is something that we have discussed earlier. So then we have this. So essentially R half is equal to S this, right. So these are the two constants. These are the two constants. So when I drew this, so essentially what we are saying is that uj by u naught, right, with respect to x by d this is actually self similar, right. So you can take these values on the y axis and x by d on the x axis, and then these are essentially, so you can take that for any of the any of the 5 jets that we are talking about right now, and those points are bound to fall on this line, which means all of them have the same B and S, right, which is the velocity decay constant, right, which is B, and So this one I should write as b is equal to velocity constant. Okay, so velocity decay constant, which is here, and the spreading rate. And we also reiterated earlier that both b and s are independent of Reynolds number. So when you go back in there and you see the different Reynolds numbers, it does not matter, right? Because that b and s is still going to be same. So if for all these the 5 jets that you have, if you were to plot uj by u naught on the y-axis and x by d on the with respect to x by d on the x-axis, then all of them will fall on the same line, or the data points can be connected by a line, by a straight line, right, such that the slope is given by the velocity decay constant b, right, and s is the spreading rate, right. Now that does not change, and that does not depend on your Reynolds number, right. So it will not depend on the Reynolds number. So you can actually use the b and the s. Okay. This is something that we had learned earlier. So essentially what we are talking about here in this particular case is that all these, so it does not matter, it actually does not matter all the major details of the thing. So if you do uj by u naught and x by d, they are actually self similar. Okay. In that case, what kind of information can I get? What sort of information can I actually get from here? Okay. So let us just say, now again for this one, if you also remember, right, we had this plot, right, for zeta, right, in this case. Okay. We also did have this plot quickly. Right. So this one was f of eta or g of zeta. Okay, this or this on the y-axis, right? Where this is an analysis we have done earlier. Right, which is equal to right on the vertical axis, and zeta, right, is equal to, and this is zeta, which is equal to r by r half, right, and it could be eta also. Or let us just say this is eta is equal to r by x minus x naught. Okay, and we found out that you could actually have a plot something like that, okay, where this one is 1, this one is 0.5, right, this is of course 0, and okay. So this one, so this is zeta, so this one zeta is equal to 1. This is zeta is equal to 2, right, and here eta is equal to 0, eta is equal to 0.1, and eta is equal to 0.2. So this is something again we had seen earlier, right. So in this particular case, right, in this particular case, now one more thing is by definition, okay, now u mean, right, what is the what is the connection of u mean and the centerline velocity. So, the u mean, right, at r half, right, is equal to half of the centerline velocity, right. So, u mean at the jet half width is actually this, right. So, in that case if I take r is equal to r half, which means that I am saying zeta is equal to 1. So, zeta is equal to 1, meaning zeta is here. So, which I can say in that case this value. So, which essentially, which basically means that you know, u mean by u naught right is about 0.5, right, which is equal to 2, right, or u mean x r half, that is what it is, right. So, it is because of r half that zeta is equal to 1 by u naught, right, is equal to half. So, you can see that that also kind of checks out, it kind of checks out. So, if I do that, right, so this is by definition, right, that u mean by u naught is equal to half. Then what is the kind of information that I can get from here at all, right? If what's the kind of information that I can get from here? So, I have the Reynolds number, I have the I have the Reynolds number that I can plot. What else can I do? What else can I do? Now, I have these two relationships, right. So, I know the jet velocity, right, I know the jet velocity. What about B and S? Do I have any ideas about that? Yes, we do, because because we have discussed it, you know, earlier. We have discussed it earlier, the typical values of B which have been found out, you know. So, it was between, let us just say, okay, yeah. So, typical values of B were 6.06, 5.9, 5.8. So, let us just say that B value is about 6, right, and S the value is about 0.1, right. So, S the value is about 0.1. So, we got 3 values there, this 0.096, 0.102, 0.094. So, it is about 0.1, right. So, these are the 2 values that, so B and S also have a value. So, we have that. We know D and we know J, right. We also know x naught. So, we can, you know, we can have some value of u naught actually, right. So, let us see what's the sort of thing we can calculate. Okay. Let us do that. Now, okay. Now, this is for the first first jet actually. Okay. So, here x naught by d is equal to 0.25 by 0.25, which is equal to 1, right. So, x naught by, so if you see x naught is what is given to us 0.25, right, d is, this is etc. 0.25, right, that is how I get that. So, x naught by d is this, right. Uj is equal to 10, right. Then the way I calculated this, the slope, I am going to just use this expression basically. Okay. Then what we do is Uj, right. So, that is Uj, which is 10 by u naught, right, by x by d minus x naught by d, which is 1, is equal to 1 by b, right, or 10 by u naught by x by 0.25 minus 1 is equal to 1 by b, or 10 into 0.25 by u naught into x minus 0.25 is equal to 1 by b, right, or 2.5 by u naught into x minus 0.25 is equal to 1 by b, right, okay. Or let us just say b is equal to u naught into x minus, that by 2.5. Okay. Now, again, so by definition, you mean x r half 0 is equal to u naught by 2, u naught by 2, right. But we can get u naught from the b here, right. So, in this case, which is equal to u naught by 2 is 1 by 2 into 2.5 b by x minus 0.25, and b, like I said earlier, is 6, but the value is 6, right. So, which is again equal to half into 2.5 into 6 by x minus 0.25. So, or you mean x r half 0 is equal to 7.5 by x minus 0.25. Okay. So, we can actually calculate the mean values at the r half, in this way, and then at x is equal to say 1.25. Okay. You mean x r half 0 is equal to 7.5. That's interesting, right. So, I can actually calculate the u mean at these values. Now, what I am going to do is going to let you work on the remaining 4 of the jets, right, and why don't you calculate the u mean values for yourself. I will come back in the next class and do that for you, right. For now, why don't you go ahead and calculate that and see what you get, right, whether you get those values or not, whether you get the u mean values or not. Okay. And you should be able to play around with this and figure out more information that you could get, and play around with these values and stuff. Okay. All right. So, I will stop here, right, and we will come back and pick it up again where we are leaving it today. All right. Thank you.